Hi everybody, I'm Jarrell. Welcome to the shop. Today's video is about f prime and its relationship to f. Click the link in the description for a worksheet with a key. If this video helps you, please like and subscribe. Let's get into it. Alright, we already talked about how to grid a function, how to decide whether a function was positive or whether a function was negative. So I want you to look at this picture right here. Okay, I got a guy about to walk down a hill. Now I'm going to do a lot of math teachers always do and sort of ruin this picturesque scene with a bunch of math. So here I'm going to draw the hill as if it were a function. I'm going to approximate it with a function. And that's supposed to be a pretty smooth function, even though I can't draw that well. And now I want to notice a couple things. First off, that function is decreasing. Okay, as I go from left to right, the function itself is on its way down. And right under the guy's feet, I'm going to draw a tangent line. And I'm going to notice that that tangent line is sloped down. And I'm going to say the tangent has a negative slope. Okay? In fact, anywhere I pick a point on this decreasing curve, if I choose to draw a tangent line there, the tangent line will have a negative slope value. And the faster the curve drops off, the steeper that tangent line is going to be. So one of the things I sort of want in your head right now is this. We're sort of kind of implying that, if I have some function and the function is decreasing, you actually write this like a human would write it. I have some function f, and f is decreasing. Then wherever f is decreasing, it looks a lot to me like f prime, the derivative, will be negative. Now, I want to talk about that in a minute. I'm going to say that, and I'm going to let it stand right now. And it's going to turn out that technically it could also be zero sometimes, but we'll talk about that in a minute. But right now, the main thing I want you to focus on is it seems like this is a pretty reasonable thing to say, that, if I have a function like this that's decreasing, the derivatives are going to be negative over that entire interval. And then just keep in the back of your mind, could possibly be zero at one point or something like that. But we'll talk about that later. Now, does the same thing hold true if we're talking about an increasing function? Well, let's see. I found another picture of a dude hiking up a hill. So, if I approximate that hill with a curve like that, and I draw tangent lines at all different places, I'll start with the one underneath his feet. That tangent line definitely is a positive slope. This one at the top, the function's still increasing, but not as much, but it would seem that the tangent line is still positive, and the tangent line would be positive here. So it seems to be the case here too, that if I have some function f, and f is increasing, then f prime, the derivative, is going to be positive. And we'll say it's going to be greater than or equal to zero. Like I said, I'm throwing the equal to zero in there part because, technically that could happen. But right now I just want you to focus on, it seems to me a reasonable assumption that when a curve is going uphill, the derivatives are going to be positive, and when a curve is going downhill, the derivatives are going to be negative. All right, so what I have drawn here is a function. And on that function, you can see on the left side of it there, I drew a tangent line. Now, you can see with my mouse here, you can see that the function is rising throughout that region. Then after it gets to here, it's falling throughout this region. The function's decreasing. And then after this point, the function starts increasing again. So let's kind of move that tangent line around and see what happens. All right, so if I move anywhere I put the tangent line where the function is increasing, the tangent line has a positive slope. Positive slope. Now you can see that the tangent line is getting less positive, but the function's still rising at that point where that is, and the tangent line is positive, has a positive slope, I mean. And then once it gets, the function's still rising, once it gets to the point where the function tops out, and now we start decreasing, notice the tangent line becomes negative, or the slope of the tangent line becomes negative. And that's true all the way through here. Then still negative, but as soon as the function starts increasing, the slope of the tangent line becomes positive. Okay, so what does all this mean for us? How do we use this to our advantage? So behind this yellow box, I got a function hidden back there. Okay, and here's what I know. I'm going to sketch a grid of f prime. Okay, now I happen to know that to the left of the number 4, the derivative is positive. And to the right of 4, the derivative is negative. Now, what does this tell me? So if I could know about the derivative like I do, if I could know that, then that means to the left of 4, I can say that f is going to be going up since the derivative is positive. That's what we've been saying. And then to the right of the number 4, notice I'm not really talking about the number 4 yet, all right, but I'm talking about to the left of it and to the right of it. So to the right of the number 4, the derivative is negative, and that tells me that the function is going down. F would be going down. Okay, so now let's actually have a look at the function. Let me just move this yellow thing out of the way, and there it is. Okay, so as you can see, when I look at this, to the left of 4, here's 4 if you can't see it, the function is on its way up. And I knew that because I knew the derivative was positive. And then to the right of 4, the function is on its way down. And I knew that because the derivative was negative. So the interesting thing here is that f prime, the derivative, changed signs around the number 4. And if you notice, if you look at the graph, when x equals 4, the function has a high point. Okay, now let's actually do an example where this might be useful. So I have this function f of x is equal to x to the third minus 3x plus 2. All right, and I have it hidden behind that yellow square. So what I'm going to do is I'm going to take its derivative. So here we go. F prime of x would be equal to 3x squared minus 3. And then that would be equal to 3 times x squared minus 1. And then that, move over to the left a little bit, that would be equal to 3 times x minus 1 times x plus 1. Okay? Now remember, this is f prime. And I'm going to want to grid f prime. I want to figure out what the signs are for f prime. Now, this obviously came out to be factorable, so I'm going to be able to do this one by hand. You'd have to do it with other methods if it's not easily done by hand, but a lot of them will be, and especially on the AP test if you're taking that. So, if I set this equal to 0, and we're going to give that a special name in a little bit, but basically then this equation would mean that x minus 1 would be 0, or x plus 1 would be 0. So that means the derivative will be 0 when x is equal to 1 and when x is equal to negative 1. Now, I'm going to refer to this later, but we call these things critical points. Okay? Remember, I'm going to find a sign grid, where f prime is positive and where f prime is negative. So before I do that, I'm going to need to figure out where it's equal to 0. Okay? So I know that this is negative 1 and this is positive 1, and that's where the derivative would be 0. So now, how is it that we figure out the sign grid? All right, I'm going to rewrite the function down here, the derivative rather. 3 times x minus 1 times x plus 1. Now what I'm going to do first is to the left of negative 1, I'm going to pick a number over in that region somewhere. So like negative 10. Now I don't have to do the evaluation, but if I plug a negative 10 in for x in both spots, okay, I'm going to have 3, which is always positive. Then I'm going to have 10 minus 1, which is negative. I don't care that it's negative 11, I just care that it's negative. And then in the other term, I'm going to have negative 10 plus 1, which is also negative. And a negative times a negative is a positive. So that's equal to a positive. So then I know all of the numbers over here, if I plug them in for x into the derivative in its factored form, it just makes it easier to do, I'm going to get a positive number. Now, the next region I got to deal with is I got to look at this region. Okay, so I'm going to pick a number in between negative 1 and 1. And let me just clean this up a little bit so I can pop that in and we can talk about it. I think 0 is a good choice because 0 is between negative 1 and 1. And if I plug in a 0 for x, if I plug in a 0 here and I plug in a 0 here, I'm going to get 3, which is positive, times 0 minus 1 is negative, times 0 plus 1 is positive, and then a negative times a positive is a negative. So I know any number that I choose in between negative 1 and 1 is going to be less than 0, negative. Now pick a number larger than 1. So I'm looking now at this region over here. And now I'm going to pick a number larger than 1. I'm going to put that into the derivative and see what the sign would be over there. So let's pick 10, pick 100, pick 1,000 if you want to. Pick something ridiculous. So you don't really care what the number is. So if I put in a 10 over here, 10 minus 1 is positive. And if I put a 10 in for this x, it's also positive. So 3, which is always positive, times a positive is still positive. So I know all the numbers over here are positive. Now what does this tell us? Well, I want to get a picture of f. I want to get a graph of that, and I'll remove that yellow square in a minute, but here's what it says. Let's go through this. To the left of negative 1, I know that f, I don't know if f is positive or negative, but I do know that it is rising. It's going up. And then in between negative 1 and 1, I know that f has to be coming down because the derivative is negative there. And then after 1, the derivative is positive, so they know that f is rising again. So I'm suspecting that this function, I'll just kind of sketch it over here, is going to look something like this. Okay? And then I know, this is sort of the important part, if you look right here, I know that where x is negative 1, the function has to have a high point. It's got to have a point like that. Because if it's rising to the left of negative 1 and falling to the right of it, well, that means that negative 1, that's got to be a top. Okay, and then the same thing goes for positive 1, except for to the left of it, the function's going down, and then the function's coming up after it, meaning at 1, I should have a minimum. So I know that. And then if I wanted to know what those y values were, I could just take negative 1, plug it back into the function, and find the y value. So let's actually have a go at this. Let me get rid of this yellow square, get rid of it, and there's the function, just like we said. At 1, we got a high point. I'm sorry, at negative 1, we got a high point. At positive 1, we have a low point. Okay? And if I wanted to know what the low point was, it looks like it's 0. If I plug a 0 in, if I plug a 1 in for x back into the function, I'm going to get 1 to the third minus 3 times 1 plus 2, which is 0. And if I plug a negative 1 in, I'm going to end up, and just do this for yourself, I'm running out of space on the page, but if I plug a negative 1 back into f, plug that negative 1 into the function, I'm going to get out 4. So the high point would be 4. So you can see, without even knowing what the function looked like, I took the derivative, I set it equal to 0, I found something called the critical points, which is where the derivative is 0, and then I made a grid, and from the grid I was able to tell which one was a high point and which one was a low point, if that's indeed what they were.